So, by the way, wala po kuhan karon video. So, pero madamo bro akong tingin, okay ra?
Yes.
Sige, so for this meeting, our discussions would be focused on the analysis of two-dimensional beams and frames, no? So maybe for frames, we'll just discuss this next meeting. So for this session, our focus is on 2D beams, two-dimensional beams. Okay, so I believe all of you are already familiar, no? Sana ang beam. Right, so now beam and frame elements play major roles in structural analysis and design. So they provide flexural rigidity, the property that the two force truss elements does not have. Okay, so for the 2D truss or for a truss element, so it's a two force member naman to axial load naman siya. No? In fact, after analyzing a truss or axial forces due to the nodal loads, which are often determined using the concept of tributary area, we then must separately consider the non-nodal loads that causes bending in the truss member. So a truss is an example of a structure where there is a procedure where this procedure is required. Now, for example, we have to consider the simple truss. Okay, and this truss is loaded with uniformly distributed load of 60 kips per foot. Okay. So assume that the total load for which the truss must be designed is 60 pounds per foot, no, of span. The nodal loads that are acting on the truss would be determined by using the loads contained in the indicated tributary area. So mura nato siyang i-divide, no? So for example, kanin siya nga case, okay, so kanin siya ibahin dire gibutang nato sa nodes, no? Sa nodes. So kani pud siya dinhi nga portion o distributary area, so kani pud siya, no? Then kaning nabilin nga tributary area dire na pud. Okay. But in reality, ang truss member is even subjected to bending also, no? Okay, so ang ideal truss is actually dili lang may counter sa actual. Now, however, the top chord members of this truss are actually subjected to the distributed load that causes this member to act as beams because may bend man siya, so meaning na kay bending stress. So an analysis that treats these members as beams is next performed. The results superimpose the nodal force solution in order to find the total axial forces and bending moments for which its member must be designed. So ideally good. So nakakay truss ng unani is subjected to uniformly distributed load, no? To which mo na siya. So ang top chord member, since it is also subjected to bending, so you have to perform also secondary analysis where you take into account the effect of the flexural stresses. Okay, so in addition to your truss analysis, no, where you assume that the loads are really applied at the joints or the nodes of the truss, and the truss member only subjected to axial forces. Okay, it would be tension or compression. So it would constitute your primary analysis, no? Okay. So note that the beam element has 2 degrees of freedom at its end. No? So if you have to consider an element of a beam, ang imong stresses karon duha gyapon, no? So bending stress and shearing stress. Okay, so if there's axial stress, then it's a frame element. Okay, so please take note of the difference. So per node, naa siya ay rotation and at the same time a translation. So and it should be perpendicular to the axis of the beam. Okay, so for example, this is your beam element. Okay, so let's say this one fixed at one end and a pin at one end. So this is a prop beam, right? Okay, so ang loads niya, so it should be applied perpendicular to the beam. Okay. All right. So every node sa beam naa siya ay 2 degrees of freedom. No? So pwede siyang rotate, nalapot siya translation along the axis na rotation. Then you also have translation. No? Okay, so there's a movement perpendicular to direction of the or axis of the beam. This is the axis of the beam. Okay. Right. So that means per node, you have 2 degrees of freedom. Okay, per node, 2 degrees of freedom. So if you consider a beam element, so there are 2 nodes. In every element, you always have 2 nodes, no? So now, if it's a beam element, so per element, you have 4 degrees of freedom. Okay, so beam element ka, so total number of degrees of freedom is 4. Okay, so you have to expect that your elemental stiffness matrix, okay, your elemental stiffness matrix is 4 by 4. Okay, so per element. Remember, mo ni ang atong dagdida, no? Kada element ka, after that, you have to combine. After you combine, you have to reduce. You solve the displacements, you solve the reactions. After that, you determine the member of the risk. Basically, that's always the procedure when you perform matrix structural analysis. Okay? Now, please take note also that sa beam, ang axial deformation is not considered. So it's neglected. So meaning if I have a force, okay, this is a beam, right? Okay, so now if I make this as a roller, that's also a beam. Correct? That's also a prop beam, right? Now, ug mingon ko nga ang akong load is kuha na siya kanang assuming ang akong load is inclined at a certain angle theta. Kani siya actually dili na ni siya matawag technically speaking as a beam. Why? Because ang atong loads karon, ang atong member karon na naman siya ay axial force, di ba? So if you take into account the horizontal component of this applied load, then by all process, this member now carries an axial load, okay? An axial stress. If there is an axial stress, that element is now a frame element. Okay, so please take note no, of the difference between a beam element and a frame element. So, let's say a frame element, so na tayo tulong ka klase nga stresses. No? So, you have the bending stress, flexural stress, you have the shear stress, and the axial stress. If wala kay axial stress, that means it's a beam element. So a beam is also, by all technicalities, it's also quite dependent on the applied load. Okay, so if it's a beam, the load must be applied. It's mandatory. It must be applied perpendicular to the axis of your beam. Okay? Now, in contrast to beam element, the frame element includes axial deformation. That's what I have emphasized earlier. Okay, in addition to the deformations of the beam, it's rotation and the transmission. So therefore, it has 3 degrees of freedom on its end for the frame element. Okay, so for a beam element, which that's our focus for today's session. So 2 degrees of freedom per node. So meaning per element, it has 4 degrees. Okay, so I think let's go straight to atong K. So ito sa atong K. Ano siya? 4 by 4 siya, but this is only for per element na to, no? Okay. So using the slope deflection equations, okay, and after that you can come up with a series of linear equations, then you can transform this into matrix forms. Okay, so you have this in your theory of structures. Okay, and this is it. Mao na ni karon. Pag simplify na to, this is now our K. Okay, elemental stiffness, okay, or stiffness per element of the beam. Okay, the good thing about the beam also in comparison to frames, ang sa beam, define ang imong access. Unlike sa one access naman siya, unlike sa frame na nanapod kay it's like a truss, no? Where you have to do some transformation because you have to be consistent with your access, no? So manang nana kay global stiffness matrix. Okay, so in terms of only one reference access, no? In most cases it should be the global access, the global X and the global Y. So mo ni karon ang atong K per element, no? So mo ra ni ang inyong input sa inyong program. Alright? Please take note of this. So if you try to analyze this, so mo na ning gi-mention kaniya nga consider na sa rigidity. Okay, unlike sa atong truss. So nanaka ani nga mga E, I, and L. I is the moment of inertia. E, of course, the modulus of elasticity. And of course, it's the length of your element or member. Okay. So, right. So kani this is for the frame element po niya, no? Frame ato na siyang i-discuss next week, no? So narita sa example ha. Una ang dimension na po sa frame na napo kay transformation kay diba if you have a member just sides up, so kung member ni mo ana kani siya lahi-lahi mo sa access, di ba? Padung dito kani po siya, for example, no? Nasa assumption ano na siya nga frame. Kani po siya nga member lahi po ang iyang orientation. So you have to be consistent, no? So you have to convert all of this in terms of one reference coordinates, and that's the global coordinate system. Okay, whereas for beams, maski wala na pa na siya, daghan kayo ng mga supports niya, no? It's only in one axis, di ba? Usa ra ka axis niya. Okay, so you didn't need this beta transformation like matrix. That's just like the one for frames and event process. Right. Okay, beam. So In this example, we have here a beam structure consists of two elements. So, kani mo ng element 1, kani mo ng element 2. No? So, element 1 na siya, ang iyang span is L, nasad. Kani siya element 2, pareha na siyang span L. So, ang EI is given, ang length is also given as just 1 inch. Now, this one is fixed here, fixed din eh. Is also fixed here. So, dire, wala ra, no? Okay. So, this is applied by a force P. So, kung ano siya, this is just like this, no? Fixed in the beam. Okay. So, kali kung familiar ka sa kuha itong theory of structures na to, no? So, you can easily solve this first using the double integration method, the Lyapunov method, the Newman equation, no? Okay, and the Poisson method, no? And a number of methods, no, to analyze this. This is obviously an indeterminate structure, no? Statically indeterminate beam to the what degree. So, beam ka, ana raman siya, no? Kana, no? Diba? So, for a beam, there are how many equilibrium equations for a beam? If we consider static determinacy, there are only 2 equilibrium equations for a beam. It's not 3, because remember, a beam has no axial stress, diba? And the load of the beam must be applied perpendicular to the beam's axis. Okay, so there are only 2 equilibrium equations for a beam. That's the summation of moments, no? So going back to our review of our theory of structures, no? And the summation of forces vertical, no? Okay. So there are 4 unknowns, right? So that makes this structure indeterminate to the second degree. That's static indeterminacy. Okay? Naiputo ang gatong indeterminacy in terms of the degrees of freedom, no, sa atong matrix structural analysis. So you can easily analyze this by simply using those methods that I have mentioned earlier. Okay? Or sayon na gid kayo, no? You can even because of symmetry. Okay, and then pass a cutting plane here, no? Then get reactions, no? The reactions obviously on the left must be equal to the reaction on the right because of symmetry condition. Okay. Okay, for element 1, itong take note, picture ninyo, sabi mo ng atong K. Sorry, this one. Okay, so for example, 12 EI-LQ, EI is 1, diba? L is also 1. So that makes that as 12, diba? Kanisad siya, EI is 1, L is 1, so 6 na siya. So if we compare it here, 12, 6, diba? And then for element number 2, makaraman gyapon siya. Same. After that, you combine. So please take note of these markers, no? 1, 2, 3, 4. This one is 3, 4, 5, 6. Ano ni mo diri? Ano man eh? 1, 2, 3, 4, 5, 6. Okay, so ang 1 is translation, 2 is rotation, 3 is translation, 4 is rotation, 5, again, translation, perpendicular to the axis of the beam, and 6 is the rotation. Okay, then after that, you combine this, muna ni karon ang atong structure stiffness matrix. Okay. Now you expect this to be 6 by 6. Why? Anong 6 by 6 man? Tanaw na to pre. How many nodes are there in this structure? 3, di ba? And per node, there are 3 degrees of freedom. So that means, sabi siya, 6 by 6, di ba? Sorry, 2 degrees of freedom per node. So, 2 times 3, that makes 6. So, 6 by 6 ang atong mao na karon ang atong structure stiffness matrix. Mao na ang atong K, no? Okay? System. Okay? So, structure natin. After that, you combine. You have to reduce by simply applying the boundary conditions. Now, kung sa man ang atong boundary conditions, okay, sa fixed-ended man siya, kani siya 0, di ba? U1, 0. This one is also 0, no? That's the left end. Right end, this one is also 0. This one, wala pa kay, wala po siya rotate because it is fixed. Okay, 0. So, mabilin kanina lang. So, meaning, I have to eliminate this. Kani, this one, kani, okay. So what is left is kanina lang siya. Ano na eh. Alright? Yeah, U3, U4. After that, masolve na nila po. Diba? Okay? Of course, you have to put the katong applied force na to direct. Okay? So, if we go back here, so may applied force na to. So, it's P. Okay? P lang. Yan, kaning atong moment, kung ano kayo apply ng moment yan, it's simple. So, muna ni karon ang atong result. Okay? So, masolve na ni nato. So, sa'yo na rin tayo. Masolve na ito ng U3, kaning U4. Obviously, wala coefficient because there is no applied moment. So, alright? So, after this, isubstitute mo magbalik din balik din mo din kaning imong nasolve, no? So, kanay 0, 0, kanay na naman ka, diba? Kanay siya is, so 0, 0, 0. So, kanay, gihatag na siya, no? Kanay, mo may mga reactions, masolve mo nila ko. Okay? Then you can solve now this reaction. This one is given. This one is also given. So, masolve mo nila ko. Okay? After that, you go back to the force displacement relationship ng element to solve the member forces. So, it's pretty simple. Ano kita siya, no? Ano yun? Solve na natin ako mga member forces. Okay. And next for the element. So, let's try another example. Well, kanisa siya, no? One, atong previous example kaniya, actually you don't need to consider a load actually on the applied force, no? Why not just consider this principle of the non-nodal forces or loads? Just like what we have discussed for one-dimensional bars, no? There are cases also the loads are not applied at the nodes. Okay, so you have to treat that as non-nodal load. So instead of putting a load on the load itself. Okay. So ang principle ni pareho ra gyapon atong ibuhat nato sa one-dimensional bars. Okay, suppose that the joints are locked before the loads are applied. This is what we do when using the moment distribution method for analyzing beams and frames. The fixed end forces acting on the members and a sketch of the reflection diagram are shown in this figure 3.9. Note that the fixed end moments, okay, for a concentrated load position are shown where A and B are the distances to the load from the left and right ends of the members respectively. Okay, so Ako na, ang kani, kung if you're very familiar with the itong mga common nga mga itong reactions, no? Okay, moments, no? Like this one, if you have this is applicable, no? So, nakakana, di ba? Kani A, this is B, di ba? Kani nga mga moments na to, di ba? Okay. Ano yung itawag mga fixed end moments? Well, if not, gamit kayo pag-matrix, no? Kaya otherwise, if you use the moment equation or the three moment equation or maybe the three moment method, ma-defeat ang that purpose po. Okay? Because you are discussing your matrix. Okay, so let's go to, pwede na sa name, memoryaho na lang sa dinid mo, no? WL squared over 12, these are mga fixed end moments, ha? Okay, AB squared over L squared, no? Okay. We have this also the theory of structures, no? Okay, so maybe you can just memorize this, no? So, but that's only for those types of nodes. No? Your node is triangular or rectangular, and you have no choice, no? But you have to analyze it as it is. Okay, let's try another example. Okay, so in this problem, we have prop beam. Okay, so fixed at one end, the other end is a roller. Okay. Now, this one is for purpose of these discussions. No? So this one is divided into two members. This is member one. From here, no? Here to here. Okay, this is your node one. This is your node two. Then member two, so from here to here. Okay, so the length of member one is 10. Take note, the units, it is in feet. L2 is also 10. 10 feet, yep. Okay. Now the load is applied at member 2, okay, at a distance of 4 feet from node 2. Okay, the magnitude of the load, concentrated load is 65 kips. Now the properties of the members are also given. So E is 29 times 10 to the 6 psi. This is the modulus of elasticity of steel. Okay, so ngayon material is structural steel. This is the modulus of elasticity. Now the moment of inertia, of course, this is dependent on the section. Okay, the size of the number. So moment of inertia is given. It's 300 inch to the fourth. Okay, so if in case in the actual situation, so you can compute the moment of inertia if you have the dimensions, no, of your section. Okay, so I believe you are really familiar on how to calculate the moment of inertia. Okay, so expect talaan, no? Pila man ang atong K sa structure na to karon sa system. Pila man atong size. Expect ta. There are 3 nodes, right? 1, 2, and this is node 3. So every node, if it's a beam, 2 degrees of freedom. So we have to expect that the 2 degrees of freedom times 3 nodes. So meaning it's 6, di ba? So the expectation is the size of the system stiffness matrix is 6 by 6. Of course, per element, it's always 4 by 4 gina siya, di ba? Per element. Kaya kada element nimo 2 degrees of freedom, and there are 2 loads per element. Okay? Okay, so ano eh? For member 1, inyo na itong i-input itong kay dere, no? Ito na itong ipapitsura ninyo. Lali ko senta, para di ko remote, eh? This one. Sorry. Ano eh, eh? Hmm? So 12 EI, just substitute, no? These values. Okay, so we can get the uh, stiffness matrix per element. Okay, elemental stiffness matrix. Let's move up to the example. Number 1. And this is now your number 2 na to. No? Okay, again, what you have to do is just to substitute your EI and R. But you have to be consistent with the units. No? Take note, this is in feet. Now the E and your moment of inertia are in inches. So you have to convert this to inches as well. Okay. So member 1, this is member 2. After that, you combine. So please take note of those markers, di ba? Pag-combine niyo. Ito itong balikod. Kani, 1, 2, 3, 4, di ba? Yeah, very good. This is 3, 4, 5. Okay? 3, 4, 5, 6. Okay? So, after that, itong 1, 1, di ba? Kani, 1, 1. Okay? So, kani gyapon siya, 60. Okay? And, if you kung pag-combine mo, ang resulta na niya should be 6 by 6 as expected, di ba? Because the total number of nodes for the entire structure, okay, or the structure considered is uh, 3, 3 nodes. And per node, nasa ay 2 degrees of freedom. 6 by 6 ni siya. Okay. Ano na 6 by 6. Okay. So this is now our force displacement relationship, no, for the entire system, also for the entire structure. After that, you have to reduce the stiffness matrix by simply applying the boundary conditions. So may mga boundaries na ito karon, let's go back to the structure, no? Okay, malipay aktualita kung daghang mga fixed o daghang mga support, no? Especially kung fixed yan. Sa conventional pa nga structural analysis, o mag-fix gani ka, that means mo increase ang imong static indeterminacy. Okay? So may tabo karon daghan ang imong mga kanang equations nga kinahanglanon. Mag-anam siya og ka-complex. Okay? Pero sa metric structural analysis, baliktad po siya. Daghan kag mga fix, mag-anam po siya kasayon kay reduce man ang imong kanang ang imong kanang indeterminacy po, no? So in terms of sa matrix nimo. Okay? So not that what I mean is the kinematic indeterminacy, not the static indeterminacy, no? So if you recall, katong kinematic indeterminacy, it is the total degrees of freedom minus the boundary conditions. Diba? In this case, 6 siya, pero ang imong mga boundary conditions karon kani 1, 2, na usa. So that means this is indeterminate to the third degree in terms of kinematic indeterminacy. So that means ang akong reduced stiffness matrix is 3 by 3 na lang kani. Okay? So kaning size atong reduced stiffness metric is dependent on the number of kinematic indeterminacy. Okay, that's if you apply the boundary conditions. After that, okay, you substitute the given loads, masolve na nako ang displacements. Ano na gina siya? Take note ha. Itong U1 translation, U2 gani rotation, di ba? So in terms of radians yan. So ang even rotation, ang add translation. So mo ni kani add man na inches, U4 and U6. That's in radians. Okay? Then once you have this, pwede na po masolve ng mga reactions by simply substituting the solved values of the displacements. Then after that, you solve the member process by now considering the considering the force displacement relationship per element. Okay. So please take note also that we consider here the non-nodal force, no? Because for member 2, okay, member 2, this 65 kips is not applied on the node of your member. Okay, so kato mogamit ka tong kani fixed end forces. Sorry, kani. Okay? Kaning mga moment PED squared over L squared. Okay? Kaning mga reactions po. So that's magamit na nimo pag-solve na sa nimo sa mga member forces mo ni sila. Okay, so by using the principle of superposition, so just like what we have discussed in detail for one-dimensional bars. Okay, so the most of the member forces you have to take into account those fixed end forces. Now, I'd like to show you the program. No? So, first. Anyway, makita na ba ang screen? Sige, so this is a sample program in Excel. So muna ang pinaka-minimum requirements ninyo, no? So this is for actually assignment 3.1. Okay, so Mao ni karon ang atong for 3.1 kani siya duha pud ni siya ka members. Okay. So kani mo ning atong member 1. Okay, mo ning inyong member 2. Okay, so kasi kani mo ni input E, I, ug L. Ang atong length sa member 1 is 120 no in inches. Okay, so for member, niya imo ra tong ipag-input kadtong mga katong mga 12 EI over L cube. Remember, no? Yan kani 6 EI over L squared. Mora ni siya 6 EI over L squared. So katong akong kuan picture ninyo, that's for muna ang stiffness matrix per element. So you consider for element 1 mo ni siya, no? Ora na i-program na ninyo. Nya karon for element 2 mo po ni siya. Take note ang akong I is 80 gyapon but ang length na ko ron is now 60 inches. But you have to be consistent again with the units, okay? After that, you have this. And please take note also of the markers, no? Okay, so this one is 1, 2, 3, 4. While for member 2 is 3, 4, 5, 6 po siya. Okay? After that, i-combine na po, no? Ang expectation na ko should be 6 by 6 po siya. Why? Because there are 3 nodes for the entire structure and 2 degrees of freedom per node. So that makes our stiffness matrix to be 6 by 6 as the size. Okay. 6 by 6, yeah. Pag combine ako, so katong using sa markers, no? So katong yes, mo niya. No. Wow. Sige. Okay, okay. Ano pa? Keyword na lang. Sige, sige. Okay, okay. Sige, sige. Sige, sige. Okay, so going back, no? So mo ni combine na to. After that, you apply the boundary conditions to get the reduced stiffness matrix. Okay? I-reduce to na po siya. So sa may mga boundary conditions na to, katong 1, 2, 0, niya ang 3 is also 0. So nabilin karon kanilang 4, 5, 6 na lang. So kani. Okay? After that, masolve na po displacement 4, 5, 6. Okay, so of course kani ipag-abutan to nimo F4 well 0 po siya, no? Okay, so wala bang kay 1, 2, wala mo kay moment i-apply din eh, no? Okay, 5 is negative 10. Okay, then wala po kay moment F6 is also 0. So you can solve now this U4, U5, and U6. This one, sorry. But I mean, kani mo ning F4, no? F4, F5, yeah, F4 na F5 siya, negative 10, this is 0. So kani naggamit ko sa mga numerical methods sa niya, no? Tapos yung determinant, so pwede ra sa ninyo dito, di ba? Katong pag-solve ninyo, sa mo to, you first get the inverse ani niya, di ba? Okay, so diba, yung anak man to, F equal to K, diba? So saan na ko pag-solve sa iyo karon? So it's simply F then inverse ako K, is it correct? F then inverse K. So ako na kong inverse. Saan ko na Expect ng inverse is also 3/3. This one, okay, butang lang na. Insert, asa ka nakita formulas. Control M inverse. Okay, control, shift, enter. Sorry, I have to get the array first. This one, control, shift, enter. Ano karon ang yan? Inverse. Oh, ganun. 3, 4, 5, 6. Ano ba yan? Ano ba yan? Inverse. 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 This one. Value, no? Change the course. Anyway, I'm going to check this later, no? But again, you have to get the inverse. After that, you multiply that by the force matrix, which is this one. Yeah, simply monitor ng atong F4, F5, and F6, no? So F5 is kanima, no? Okay, so ang akong F4, wala man kay force diya i-apply, di ba? So F5 na ko, wala pud ka, no? Sorry. F3, 0, F4, wala man kay moment diya nga i-apply. This one is 5 and 6. So 5 is negative 10. Okay. And then F5, yeah, wala kay F6, no? Which is 0, wala man kay i-apply ng moment. Yeah. So that's why this is 0. This one is also 0. Okay. So this one is 10. You have to be consistent the units. That's why it's 10, negative 10,000. Negative 10 because it's going downward. So morning karon ang akong this one. U4 is morning rotation. U5 is displacement, negative. U6 is we have also the rotation, no? Okay. Na may mga rotation sa akong load. Okay, so it's quite simple. Let's have another example. Clear the drawing. Mulain din 3.7, for example. 3.7, let's go to 3.7. Oh, this one is for frames. $3.4. 3.13. We're using nonodal force. So this one, so 2 members gyapon. So mo yung result karon. Okay, so per member, number 1, this is our member 2. Then after that, you combine, so you apply the kaniya kung paano na apply na to sa nonodal force na to. So 1, ano mo siya? 1, 2. Kani 3, 4. Kani 5, 6. Okay, ang 1 na to 0, di ba? 1 na to 0. Ang 2 na to mo rotate. So meaning na siya rotation. Ang 3 nako 0. But ang 4 nako rotate po siya na mo tuyok man it's not fixed, di ba? 5 nako 0. So kaning akong 6 mo rotate ya po siya. So kung nabilin karon is kanin lang U2, U4, U6. Mo ni U2, U4, U6. Kani mo ning akong F2. So may apply na ko sa F2. So katong mogamit ko sa katong fixed end forces, no? Muna na kani F4, so fixed end forces gyapon, and also your F6 na to. Okay, so after that, masolve na sa mo ang imong displacements. Okay. After that, once you have the displacements, you can go back to the elementary stiffness matrix kani. Okay, may masolve na sa mo. Please take note na kay mga fixed end forces diri. Why? Because if you look at the kuha na to kaning atong members na mga non-nodal forces niyan. In other words, the loads are not applied at the nodes. Okay? So you have to consider katong force sa kani, W squared over 12, kani PAB squared over L squared, no? PAB squared, PE squared B over L squared po ng mga moments na ito. Right? So, muna karon ng atong mga member forces. Of course, you can check this by simply going to the equilibrium equations, no? And draw the key body diagrams. Alright? Okay. So, kani, I don't know ano ini siya. Okay, F. Well, supposedly, we have to get what's that, may pangbutang dre ha. Kasi yung dito ano. Okay, sleep on sa ano. Proceed. Control Z, wala tiguan may pinapalimot. In short, that's one to on. Kasi itong functions na po. And inverse. To get this away. Ano siya mo tatap ng inverse. Control shift enter ba no? Control alt enter mo na akong nakuhan. So siya na. Tama nito. Okay. Release kanina. Yeah, control shift enter eh. Shift enter. Control shift enter eh, no? So, napislit na ba niya? Control out, enter. So after that, emote na yun ko, no? So, continuous with filter. Oh, naday sa'yo, Pleta, no? Ah, sorry, worse na naman to. Continuous with filter. Ano na siya, no? You can compare this morning, no? Kani o kani, no? So, morning, satu, kanina sa F, di ba? F, K, umuling atong F karon kani. Kani mo atong K, kani, no? This is our K. Kani mo atong dismiss. Morning akong kaon, di ba? So, it's mo siya, no? So, atong buhaton, so, kaon atong inverse, then you have to pre-multiply, no? Pre-multiply ta kana F, kani, inverse, K, no? So, kani, unit matrix, di ba, no? So, ang akong displacement matrix, so it should be the inverse times the force matrix na to, no? So, morning inverse na po, you multiply this by kani, so, mo na ni karon atong makuha. No? Okay, so ganana lang, no? Kani akong gi-program, no? So, using some methods from the numerical, from some numerical methods. Okay, so going back to 3.1, ato itong balikon, and control shift enter dito, no? So, sa ta. Ako na siyang ituyo para hindi mo makalimot. So, kami, nasa na ito dapit? Inverse, and inverse, kami, control shift enter. So, na siya value. Then after that, multiply na ko ang remote na matrix multiplication. So, K, di ba? K inverse times the second array katong force. Then control shift enter. Mo na ni compare ni mo oras siya, di ba? Alright? So, ano na gyud? Sayo na gyud kayo. So, every element, after that, you combine, you reduce, you solve the displacements. Very simple. No? After that, dahin ka, no? Solve mo na nimo ang imong mga member forces. So, may consider the elemental. Mora magyapon ni siya, no? Wala mo na no sub na. Mo, that's the same because that's a beam, di ba? You don't need to, wala mo kay mga transformation matrix na imong buhaton. Yeah, just one lang, no? Kani mga fixed end forces. In this case, ang member 1, wala mo kay fixed end forces. Diba? Sa 3.1, wala mo kay fixed end forces diri. But here, wala gyapon kay fixed end forces. So, 0 na gyapon. Okay. Alright. So, do you have any questions or clarifications?
Sir. Okay, question, sir.
Yes.
Sakto ba, sir, na ang katong Cramer's rule kay mo tong pag-reduce sa ng matrix equation katong ipang-remove ang mga zero?
No,
Zero.
dili siya. Wala na siya ilabot. Actually, ang pag-solve lang nako sa displacements, no? ang kaning Kramer's rule. Ang pag-reduce nimo kanto lang i-apply the boundary conditions, di ba?
Okay, sir.
Katong kani U1, U3, U4 katong i-discuss na ko ganihan. No? Okay? Kani for example sa 3.1 kaning di ba? 1 1 2. Ana mo na pag imong 1 3 4. Yeah. 5 6, di ba? Ang 1 nimo 0, right? Wala man na siya mo di man ka mo sa support. Kani fixed end pod U2 nimo is also 0, right? Di man siya mo rotate because that's fixed end. U3 nimo is also 0. Wala siya translation or displacement along the vertical because it is fixed. But U4 nimo naa ka, mo rotate siya, di ba? Kaya this is not fixed end. So naa kay 4. 5 sad, of course, mo displace na siya. Mo na support, ang 6 mo rotate po na kung wala siya support. So, mo ni 4, 5, 6 na lang siya. Mo ni pag-apply na ko, kanina lang nabilin 4, 5, 6. Okay, U1, U2, U3, 0 siya. So I have to eliminate the rows and columns that corresponds to this 0 displacements and rotations. So, mo na ni karon. So it's either you use Kramer's rule. Kani siya is kuha na siya. It's another numerical method on solving the unknown, no, for matrices. So kani, instead of using Kramer's rule, dali kayo, gamit lang ko sa Excel using inverse. After that, you multiply this you multiply the force displacement from your inverse of your stiffness matrix to get the displacement. Okay.
Sir, kanang negative 10,000, sir, and input na siya, sir.
Input ni siya kay man eh. Nawa, ang imong force karon, unsa may imong force sa 1? Reaction man nimo, di ba? No? Reaction ano mo, ang imong force sa 1, reaction to which ano na siya actually, no? Ang imong force sa 2, anon po na siya, no? Mao man imong moment. F2 kani siya mo ning imong F1, no? So, imo solve mo nimo siya, no? Ma-solve na nimo once you have the displacement. Ang imong F3 is also reaction po ni siya, no? Okay? Ang imong F4 wala ka, no? It's 0 na siya. Wala mo kay moment i-apply. Ang imong F5, ni. F5 nimo, it's negative, no? So, F5 nimo, naman sa F5. Yeah, ang imong F6 po, no? So, F5 nimo is negative 10. Ang imong F6 is also 0. Wala mo kay moment i-apply niya. Now, kaning F3, F1, o F2, these are the reactions. You can solve this once you have the displacements, di ba? Once na nakaani, U4, U5, U6, i-substitute na mo din eh, no? Ganun. I-substitute na nimo kaning F4, 0, o man eh, F4, F5, negative, gani. Once you have this, okay, kaning U1, U2, 0 na siya, masolve na nimo F1, F2, F3 nimo by using kani tanan. Okay, meaning kani, ako ning i-multiply ani, ina naman ko is value sa U4, U5, U6, U1, U2, U3 are all 0. So, masolve na nina ako kani. Okay, these are the reactions. One ang ako mga reactions.
Okay, sir. Thank you, sir.
Sige, sige.
Hello, sir. Pwede mo
Yes.
clarify about sa assignment, sir?
Yes.
Sir, if okay ra nimo sir, ganahan unta ko mo clarify, sir, about sa usa ka answer sa answer key gani, sir, sa 1.13.
1.13, niya.
Ang beam, ang letter C sir, sa 1.13, letter C, ang katong beam, ang iyang kinematic indeterminacy.
1.13. Kani? This one, yes.
O kana sir. Dili jud ko sure sir, pero ang ingon magod ang answer key kay ang K daw equals 0. K equals 0 ba jud siya sir? Make sure lang ko sa kanang beam ang iyang kinematic.
Kaning beam, kinematic,
Yes sir.
determinacy. Okay, so pila man ka degrees of freedom tanan? Kung beam ni siya, so 8, right? Is it correct?
1, 2, 7.
So puro man ni ruler, no?
Yes sir.
So that means 8 ang iyang total beam ni siya. Okay, beam, yeah. So 8 ang iyang total degrees of freedom, yeah. Karon ang iyang mga boundaries. So kani is 2, 3, 4, 5. So 3 siya, 3. Ang imong kinematic indeterminacy. You have to expect na ang imong reduced differential to be 3 by 3. Ay mo rotate sa din eh.
So K
Rotate, ha?
mausad akong nothing sir tungod kay naay rotation kada roller, so
Ano
K
yung kada
equals
roller?
3 sir, pero ang answer
Unless kung ipang fix mo na siya, no? But that's a roller. No?
pero roller man sir, so di ba kanang
Yeah.
naray rotation diha.
Yes, yes.
Sige sir, kay ang sa answer key man god sir kay K equals 0 niya akong makuha jud sir. Then I think some of us sad sir kay among makuha jud kay K equals 3. So naglibog mi kay niya ang answer key K equals 0.
Okay. Unahin lang siya, meaning mo rotate, yun na siya, di ba?
Saka sir.
So, that should be, kuhan, that should be 3. Yung kinematic indeterminacy.
Sige. Thank you kayo sir for the clarification.
Any other questions? So, next week, kanto na po tayong frame. So, frame, mo lang yapon, ang imo lang kuha na to, murag trust, kinahanap kay, imo na sa siyang i-convert, okay, ang imong access into kuhan, into global. So, na kay transformation matrix, okay? So, because you have to be consistent with the kuhan, itong stiffness in terms of one kuhan siya, kanang coordinate system, that's the global. Yes. Uy, may plans next week. Oh, okay, Mayo. So, malipay mo. Ano? Malipay ko. No? So, next week nilang na mag-klase. So, for the assignments, I have to, yes. Sige, tama. Sige, sige. Sige, we still have to figure out sa katong one, canvas, sa unto pag one, adjust, no? Okay. Sige, palihog ko ha. Ikaw lang mo ipano na kami ha. Para take charge na. No? Just give it to me para it would be fair also to yung squad, no? Attend the class. So definitely you have to take that into consideration. No? So please, na lang kanang take charge na nada, no? Kay mga tataon na ba yata sige kuan? Wala tapos sa attendance. Sige, salamat ha. Thank you. Thank you. Thank you. See you next week. Salamat.